Well, people have been turning off my lectures, so I figured I'd better start out with some jokes this time so you'll listen longer. Classroom principles. You need to learn these for class, right? Murphy's Law and other related theorems. Murphy's first law, I always give this in my classes because it always happens. If anything can go wrong, it will go wrong. Murphy was an aerospace engineer. I've been in aerospace engineering too. And this is very true. In aerospace engineering, everything has to be perfect. If anything can go wrong, it will go wrong. So you always fix the missile so that there's nothing that can go wrong. That's what happens in the classroom. Proofs, the errors on the first step, right? Every time you make a mistake in your proof, you have to do the whole thing over. Theorems. When you come up with a new theorem, always remember this. If true, then not new. If new, then not true, right? That's the way most theorems work that you come up with. Exams, you've done this before, right? You always figure it out after you finish the test, right? You always catch on after the test. And furthermore, in the final exam, all questions required ratings, but your calculus was in degrees mode and every one of them was wrong, right? Homework, your dog eats it. This is the way life goes, right? So we'll try this today. Maybe we'll see a few examples of that. Every answered question generates at least two new questions. This is always true in mathematics. It becomes exponentially more difficult every time we get another generation along. Research, enough research will tend to support your theory. You've seen that in politics all the time, right? Pencil sharpener is always broken. Bad luck to sit by the trash can. People always miss. Murphy's laws were named after, was an optimist. All right, so let's get started on the actual material before I lose you again. Today's topic is linear differential equations and of first order. And so this is out of a chapter on first order equations. Here's a linear equation in standard form of first order. dy dt plus p of ty equals f of t. This particular form is very important for our existence and uniqueness theorem coming up. If p and f are continuous, this can always be solved. This is actually partly the existence and uniqueness theorem, at least in terms of integrals. It comes out always to have this solution. You let mu of t be e to the integral of p of t, where p of t is the function that multiplies y. Then y is 1 over that function times the integral of that function times f of t to the right-hand side dt. Every linear first order equation in standard form, this, always has a solution when p and f are continuous on the solution interval. And it's this, let mu equal e to the integral p of t dt. Y is then 1 over mu, integral mu times f. Works every time. Can't always do this integral exactly, but when you can, it's still very important as a theoretical solution because the computer can estimate this solution when you're also given an initial value. So here's the derivation of that. I think the derivation is important because this is the way people solve it. This is the formula to solve it, but just as commonly, people solve it by the derivation of the formula, which is this. You calculate mu equals e to the integral p of t dt, where p is the function that multiplies y in standard form. And you multiply through the differential equation by mu. Mu is called an integrating factor because it makes it so you can integrate this. When you multiply through, look what happens. The left side becomes the derivative of mu times y by the product rule, right? Going backwards. The derivative of mu times y is mu times y prime plus mu prime times y, right? Derivative of the first times derivative of the second plus derivative of the first times the second. That's what this is. So multiply through by mu, whose derivative is p of t times y, if you think about it, right? If mu is this, the derivative of this is of e to the whatever v is e to the v times derivative of v, but derivative of v is p. So p times y is the derivative of mu. P times mu is the derivative of mu. And this left side is just the derivative of mu times y. And you have mu f on the right side. So now this can be integrated because it's a derivative, because we call mu the So we integrate both sides. The integral of the derivative is just y plus a constant, but I'll carry that over here. Equals the integral of mu times f. Right? So integral of the left is y, integral of the left is mu y, and then you have equals integral of mu times f. Then you divide it by mu. So you integrate and divide by mu, and you get 1 over mu integral mu f. And now you got it. That's the solution. That wasn't so hard, was it? You just multiply through by mu, recognize the product rule, integrate, and divide by mu. And there's the derivation. There's the proof of the theorem. Let's try this linear differential equation. Suppose I want to solve this linear equation. How do I know it's linear? Because it's a function of t only times dy dt plus a function of t only times y equals a function of t. So it's automatically linear. Right? Let's try it that first way by multiplying by the integrating factor rather than using the formula. And then we'll try the formula. This is much like algebra where you could solve a quadratic equation either by completing the square or by using the formula that's proven by completing the square that we call the quadratic formula. So we could either complete the square or use the formula, the quadratic formula, to solve quadratic equations. And similarly here, we can either multiply through by an integrating factor or we can use the formula. And just like the quadratic formula, you can easily make a mistake if you didn't start out with the quadratic equation in the right form and try to use the formula. Similarly here, you have to put this into standard form or the formula doesn't work. This is the biggest drawback. People try to use the formula without getting into standard form and it fails, right? So first you divide through by t so that the lead coefficient is 1. So I divide through by t and get this equation. Now the lead coefficient is 1. Now I can apply the formula, not before, right? So the formula says I take e to the integral of p of t, this function that multiplies y, e to the integral of 2 over t dt. That's going to be my mu. Well, integral of 1 over t is natural log of absolute value of t, so I have, and the 2 comes out of the integral, so it's e to the 2 ln t. But I can put the 2 up in the exponent by properties of logarithm, right? This is e to the ln of absolute value of t squared. E and ln are inverse functions. They don't do each other. So I get absolute value of t squared. Well, absolute value of t squared is the same thing as t squared, right? So we get then the integrating factor is t squared. So now I take the equation in standard form, this one, and multiply it through by t squared. I get t squared times dy dt plus 2t equals t cubed. When I multiply this by t squared, the equation in standard form, the integrating factor multiplying that gives t squared dy dt plus 2ty equals t cubed. According to what we said in the proof, the left side now has to be the derivative of a product of mu times y, t squared times y, and we can check it out. Derivative t squared times derivative of y plus derivative of t squared times y. Sure enough, this was the derivative of t squared y by the product rule. The right side stays the same. Now we integrate this equation on both sides. You get t squared y equals t to the 4th over 4 plus c. Divide through by t squared and get y equals t squared over 4 plus c over t squared. This is what we call the general solution. It's the form of all solutions to the linear equation, written in terms of an arbitrary constant c. So there's all the solutions to the linear equation. And now, having done that the long way, like completing the square and solving a quadratic equation, we could have just gone to the formula for this, just like we could have gone to the quadratic formula for a quadratic equation. Suppose we instead computed mu equals e to the integral p of t dt is t squared. And by the way, why don't I put a plus c on here? It's because I can, it doesn't hurt anything. What you want is any integrating factor. So you can put the plus c on and do some extra work. It will still work. You'll carry an extra c here and it'll all cancel out and you'll get the same result. Or you can just choose c equals 0 and say, I'm going to choose the integrating factor with c equals 0 and save yourself a little writing. Alright, so I'll pick t squared with c equals 0 and say the solution by formula is 1 over t squared integral of t squared f of t dt, right? Just putting in the formula with t squared for mu. And now integral of f was t, and so I have to integrate t cubed. I get t to the 4th over 4. That multiplies the 1 over mu squared. You multiply it all out and you get the same general solution with a lot less writing, right? So there it is, solving this by finding the integrating factor, multiplying through and integrating, and then by the formula. Here's another one. Suppose I want to solve this linear initial value problem, right? A function of t times dy dt plus a function of t times y equals a function of t, and there's supposed to be a semicolon in here. Together this time with an initial value, y minus 1 equals 1. This will get an infinite number of solutions with an arbitrary constant c, then we'll apply this initial condition and wind up with the unique solution to this initial value problem. There will be just one solution. So we must put this in standard form to apply the formula, so we multiply through by t this time and get this as the equivalent differential equation where t is at 0. They'll be equivalent. Now I use the formula mu equals e to the integral p of t dt is e to the minus 3t. And I use the formula 1 over mu integral mu y mu f dt. And this integral requires an integration by parts. You can put u equal t and v equal e to the minus 3t dt. Integration by parts does this for you, the t e to the minus 3t. And you just multiply this all out. Here's the general solution of this differential equation by formula. The fast way is c e to the 3t minus t over 3 minus a ninth. So this is all solutions to differential equations. Now you plug in the initial condition. When t equals minus 1, y has to be 1. So you plug in minus 1 for t here, and you get minus a third, minus a ninth, or minus a third, minus a ninth. And you plug in 1 for y on the right, and 1 has to be equal to a third minus a ninth. So c must, times e, and also the c e to the minus 3 plus that. In order to make these two sides match, it must be that c is 7e to the minus 3, 7e to the 3 over 9. So in other words, this is 1/6. You subtract it over here and get, this is minus a 6, is it? Oh, that's right. I may have to fix that. That might be. So this is 6 ninths minus a ninth is 5 ninths. Subtract it over and you get. This is 3 ninths. Minus a ninth is 2 ninths. Oh, this is okay. 2 ninths. Subtracted from 1 gives 7 ninths. And so C has to be 7 ninths e cubed. That is correct. Okay. So C is 7 ninths e to the 3. Then you put that back in for C in the solution set, and you get the unique solution. 7 ninths e to the 3t plus 3 minus t over 3 minus a ninth. Now it's worth making an interesting point here. If you can't do the integral, you can still write the formula for the solution. In that case, given an initial value that y of t0 equals y0, like this, the formula, if you use for your integrating factor, you can use any one you want. Suppose you choose the integrating factor from t0 to t of mu of t dt. By the fundamental theorem of calculus, this is one integral, and it's the integral whose value at t0 is 0, and you can write out a formula for the solution that also includes the initial value, and this is it. If you make the integrating factor the integral from t0 to t of p of t dt, I've changed it to tau. It's supposed to be a mathematical faux pas. I use the same variable here as you do at the endpoint as y, but it's the same integral. Integral p of t dt, evaluate at t and t0, take the difference. If you plug that in here, this gives you the unique initial value system, initial value problem solution. So we can apply that to this problem. dy dt equals 2t times y plus 1. This is actually a linear equation, right? If you multiply this out and group it over, this is dy dt minus 2ty equals 2t. And now, see, it's a function of t times dy dt plus a function of t times y equals a function of t. It's linear. And it's in standard form because the coefficient of dy dt, the highest derivative, is 1. But it's linear first order in standard form. You take the integrating factor as e to this function, integrated. But this time we'll go from t0 to t, goes from 0 to t, and we'll get e to the minus t squared. So this is the integrating factor for our formula when you're given the initial value. And then you plug that into that formula. Let's see, that was u was e to the minus t squared. And I'll put it in here just with a tau since I'm getting here, let's pick a tau. And I'll go from t0 with the initial value point 0 to t. And when I do the integral, I'll leave that out. But turns out you can do this one, it's e to the t squared minus 1. But if you couldn't do the integral, you could still leave it in this form, and computers can estimate these definite integrals very accurately for nice functions like this. So you can get a pretty good estimate on the computer is the point. But also this shows you that you can get the exact initial value problem solution by that formula if you want. All right. That's the material for this section. It's just linear equations of first order. It's very easy. You can multiply by the integrating factor, integrate, and if there's an initial value problem, plug it in. Or you can go straight to the formula if you make sure it's in the right form. Try some of these problems and see if you can do them.